Hello and welcome to our Tips and Techniques videos. I'm Mark Biasotti and we are currently in our advanced modeling episodes. And over the next 30 minutes or so, we'll be exploring how you can increase your skills using some of SolidWorks' more advanced features so that you can be more productive and create higher quality models. So whether you're a seasoned SolidWorks user or a beginner, we think that you'll learn something new in this series. For your convenience, we've listed the topics in the YouTube description that we'll be covering in today's episode, along with a timestamp for each topic in the video. Feel free to skip ahead to any tip or point you want to learn more about. This series is being brought to you by Spanner Product Development, a product development company dedicated to creating positive impact in the world, merging innovation, sustainability, and responsibility to bring meaningful experiences to life for over hundreds of clients. If you want to learn more about what Spanner has to offer, stop by our website at spannerpd.com or email us at hello@spannerpd.com. Now let's get started with this episode of our Advanced Modeling episodes.
Welcome to our SolidWorks Tips and Techniques video series. This is episode 5. Advanced Modeling Part 1, and we'll be doing a number of different advanced modeling episodes over the following weeks, but I thought I would start off our first episode in this area talking about the differences between basic modeling and advanced modeling in SolidWorks. Now that subject has a lot to do with what industry you are in. For a lot of you, I know that you're in machine design and you rarely do any advanced modeling. For consumer product design, for those of you in that industry, you're probably doing a lot more of this, and that's where this episode in this series probably piques your interest. But for all of us, we occasionally have to do some advanced modeling, even if you're not in the consumer product industry. For these episodes, we're going to talk more about what's required from SolidWorks for the consumer product industry, because that's where you really probably have to apply more advanced modeling than you do basic modeling. So over the next 30 minutes or so, I'm going to try to introduce some of these topics that have to do with this subject, and it's kind of a smattering of different important points when doing advanced modeling, and I'll try to walk through them one by one. So this slide is somewhat representative of consumer product design, at least the consumer product design that I'm involved in. Regardless of what you might think, I don't have a penchant for black products. It's basically what I've just grabbed recently, and it's a trend actually currently. But those trends will change over decades. They'll swing back and forth to white products, to metallic products, to black products, to brightly colored products. There's one trend that's pretty universal over the last 40 or 50 years, and that is when it comes to consumer products, and especially high-tech consumer products, the mixture of different materials is always something that distinguishes the product to be of more value. When you have a mixture of a textured plastic along with rubberized overmold and some metallic surfaces, they generally come off looking just more expensive, more high quality, and that's a kind of universal appeal for people and for companies to distinguish themselves from their competitors. So because of those materials, this is why we have to pay special attention sometimes to the way that we model, because those surfaces tend to show off or reflect their environment to a much higher degree than maybe just a beige textured product. A good example of that, I could bring up an example model, and that would be This familiar object, this is the iPhone, which was introduced in, I think, 2007. This is the original form for it. And what you see here before you is two different approaches to executing the iPhone. One is using only basic features, that is extrude, revolve, fillets. And the other one is to use more advanced features like boundary surfaces, sweeps, C2 fillets. Now, can you recognize the difference between them? Probably not from the front, because from the front of an iPhone, it's fairly prismatic, with the exception of the corners. But you do have a flat screen and you have some pretty prismatic features there. But if you turn it over and then start moving it around in the light, can you see the difference? So I'll point it out to you if you can't. Here on the left is our advanced modeled execution of the iPhone. On the right is a basic execution. And can you see how the light plays across the back? I mean, these both have radiuses and they both have soft edges, but if you look at it with some reflections on in real view, you can see there's a dramatic difference on the way that the back connects to the side rolling surface. Here you see there's a more of a hard edge reflection, and that's because everything on this phone here is done with basic features and just tangency. Then on the left here, we've executed it with curvature continuity, and I'll get into this a little bit later in the episode. But not only the way that it looks, but the way that it feels is very important. And of course, holding this in your hand, that's of real high value to be able to execute your models that not only look good with lots of reflective light, but also feel good. And our hands are very sensitive to these nuances and differences. So that's probably a good example of what you have when you try to execute in one technique over the other. And that's actually a pretty worthy attempt there, but you can see the differences. Okay, so this next slide brings a lot of smiles to people who know me. But for my colleagues, I always tell them to avoid surface modeling at all costs. And what I mean by that is that because SolidWorks is a hybrid surface solid modeler, there's a lot that you can do with consumer product shapes using just basic modeling features. Or the majority of what you can do is done with basic modeling features, and then there are some advanced modeling features to complete the form. The reason that I recommend this is that we all need to know that surface modeling generally requires a lot more successive features to complete the overall shape, because you're putting it together in somewhat of a patchwork to achieve the overall form. Whereas in basic modeling, that's not the case. You get a lot more macro features with solid features to complete what you have to do in surface modeling, which is put together all those parts to make that solid form, if you will. Also, it takes a lot more care to manage those surface features because they have a lot more that can be manipulated with them, especially if they're created with curves. You have to define the boundaries of the surface. For instance, if it's a boundary or loft, or if it's a sweep, you have to manage the path and the profile, and then optionally guide curves to make that shape. They're also more susceptible to parametric change because there's a lot more versatility in surfaces. There's a lot more that can parametrically change. You know the saying that less is more. Well, less is more in solid features because because of what I mentioned earlier, that they're a macro feature of a surface where you define a few parameters, and because there's so few parameters, there's less to actually go wrong. With surfaces, there's a lot more individual edge and surface IDs that need to be tracked, especially as you build up that patchwork of different shapes to make that overall solid model, which is your end goal, of course. They're also more susceptible to interpretation because they're not just primitive shapes, they are advanced shapes. And when they're advanced shapes, they can take so many different more forms than a primitive shape. And because of that very nature, they're going to take a lot more work to get right, especially if your client is critical, and if your client is an industrial designer, they'll probably be critical. So you need to really tweak on those shapes to get them to what the form is representative in your client's mind. And then lastly, they just take more time to create because there's more to do, and because of all these prior bullet points, you're just going to spend a lot more time modeling and surfacing than you will solids. I mean, a lot more features, a lot more interpretation, a lot more change or correcting errors because of the many more features in your tree. To start off with, it's always good to strategize your plan of attack. And what I mean by that is to, in advance, think about how you're going to execute this modeling, especially if it's an advanced model and product. It's really pays off to do this planning. I mean, no one would build a house without having plans and doing environmental considerations and taking many things to an account before you really spend a lot of time and money building it. And the same is true when doing these kinds of products in SolidWorks, especially very advanced models and consumer products. So it's always good to, if you're working in a team, to understand who is DRI, or directly responsible individual, for what is going to be worked on. Oftentimes you have an author who's kind of the lead for the master model, and that person needs to take ownership and maintain ownership of that. That will be driving a lot of derived parts. And then as you have individual team members working on those derived parts, they need to understand how they relate to other team members working on other parts of the program. At Spanner, we use flow diagrams like this one oftentimes in the beginning so that everyone is on the same page, that there's clear communication about what's involved. It's also extremely valuable to be able to build the BOM up front with flow diagrams like this, and so that there aren't surprises downstream where there's lots of investment and then some of that investment is wasted because we didn't think about how the overall plan of attack would go up front. So it's important to lay out the units and the part numbers. Of course, that'll help a lot. To have a parts number list. It's also helpful to discuss, well, what are the risk features? What are the areas that are really going to change? Which are the difficult features that need to be really understood and tackled first? In our industry, because concurrent engineering goes through a number of phases, towards the beginning of the phase, a lot of us work in what we call sandbox mode. And what I mean by that is that we will first work in kind of an isolated mode where we can do a lot of experimentation. And that's important because that's where you're doing a lot of problem solving. It's where you don't want to invest a lot. And then as you move forward to architecture, detailed design, DVT, EVT, and the production, you're going to get more and more invested, and that's where you want to kind of solve the risk or minimize the risk as you move more into those areas. So you want to not also put off the difficult. It's tempting to just start modeling and, oh, we're going to see how it goes and it's all going to work out. Well, that often is just a dream. It really pays to tackle the difficult stuff up front. That's kind of my motto is, and what helps save me a lot from difficult problems is really tackle the hard stuff first. And as I was saying with sandboxing, it's really good in the beginning to work in an agile mode. That is, to sketch out ideas, maybe even without even doing CAD. And I really highly recommend this. This is a temptation for a lot of us to just go in and start modeling in SolidWorks. But you're starting to invest in something, whereas if you had a notebook and did some sketching, you could do it much more quickly for yourself to try to visualize how you would build this model. I'm not talking about just how the shape would look, but I'm talking about how would you actually execute that shape, and using a notebook to try to capture your strategy. Am I going to be able to build that with a revolve or an extrude? Do I need to use a boundary surface? Do I need to do a sweep? And then just kind of understand the trade-offs up front. And then, as I said before, work in a sandbox and work very quickly. Don't invest a lot, don't constrain a lot, but do very small experiments and move on until you have something that you feel is going to solve your problem for executing this shape. And then you can move into something more formal and something more into SolidWorks. You also don't want to make assumptions. This is something I've done a lot, and I've learned from it, and I see a lot of other people do. They assume by looking at forms, especially when bidding a job, like in our industry of product development, the forms initially look very simple, but if you look more closely and you think more about how they are to be executed, they turn out that they're not. They turn out to be pretty complex. And there's some gotchas and some surprises in product design. I mean, frankly, that's why I enjoy working in this field, because there's always a problem to solve, and it's a field where you need to be highly creative to solve the many vast different shapes that are presented for us. So another topic that is key to advanced modeling, and it's one that will come up and is often asked, is understanding the differences between how surfaces are connected. And I have this little model that I've used over the years that helps explain that pretty well. And we're going to talk a little bit for a couple minutes about what are the differences in how surfaces are connected, whether they're tangent, C1, C2, C3 or better, or in some industry it's G0, G1, G2, G3. So with this actual SolidWorks model, I've illustrated how you can see these over kind of this graphic of these different letters and these different versions of the C. So if we start on the left here and move to the right, what we're visualizing here, and this is actually a SolidWorks model with SolidWorks curves, and with those curves I've turned on the curvature combs, which is a feature in SolidWorks to help us visualize the rate of curvature change over any given surface or surfaces. So what you see here, which is referred to as C0, is a C0 connection. That is where two surfaces meet. but there's no tangency. There's usually a hard edge, and you can see that the rate of curvature is different for each, and they're by no means connected when it comes to any continuity or tangency between these two surfaces. So that's known as C0. If we move on to C1 and up the ladder, basically when we do make a tangent connection between two surfaces, as is this radius and then this arced upper area of the C, we have what's called C1. And a C1 condition is where you have tangency, but you do not have curvature matching. And then with a curvature comb here, you can see that we have a rate of curvature over this arc surface, and then we have a different rate of curvature here on this radius. If, by the way, if the sides of this C were just linear or flat, you would have no rate of curvature because there'd be no curvature change. You would have no curvature comb showing because the curvature would be infinite or zero. Then moving on to what we refer to as C2, this is curvature continuity. This means that where two surfaces meet right here, that we have equal curvature. That is, the rate of curvature here on this arced surface is equal to the start of the rate of curvature here on this radius or C2 fillet. Now, there's a lot of confusion about C2 because people see they turn on their curvature combs and they see this, and they see it and they assume that does not look very curvature continuous. But in fact, it is curvature continuous because where the intersection is between these two surfaces, the curvature is equal. So we call that curvature continuous or curvature equal. Now, when things get really interesting and is when you move to above C2 to C3 or higher. And so what C3 means is that you now have equal curvature, but you have some gradual transition of that curvature as it crosses over the boundary between the two faces. So here you can see we have the same rate of curvature as the last model, but I've tweaked the corner to have a C3 or a G3 continuity so that as it can transition its curvature from that constant rate of curvature of the top surface into this corner. And you can see the curvature combs and how that is displayed there. Now, you can go to higher rates, C4, C5, but they're essentially just C3, but with more of a gradual transition between their two connected surfaces. So why that's important is because when we execute models, whether they be tangent or they be C2 or C3, certain products will really highlight or show off that difference. Three very simple examples here are automobiles. So when you have an automobile on the showroom floor, it usually has spotlights from the ceiling, and sometimes it's on a turntable. And because it's turning, you get to see how the light flows over the car. And this is its selling point. It's gorgeous. It's beautiful because of the way the light is highlighted over the body. And it is the reason why that automotive designers don't use fillets. Fillets are, again, a tangent connection. So they'll be very meticulous and careful to not use fillets, but they'll do G2 and G3 connections between all the various surface parts of the body of the car. And when you do that, then you get a very dramatic and different effect over how the car looks, especially if you're in that scenario where it's in a showroom with lights on it and on a turntable. But this also applies to the consumer product industry too, for products like smartwatches and appliances, where a lot of times you have highly reflective surfaces, whether it be metallic or gloss white or gloss black or glass even. The way that you construct those shapes using those materials will make a huge difference. As you can remember from my previous example with the iPhone, it's just further magnified in the consumer product industry for many products. So that is why the connection between surfaces is so important and something that you want to constantly keep in mind. Now, a basic overview of when I talk about basic modeling and advanced modeling, and by no means is this fully conclusive of all the features in SolidWorks, but some of the basic ones when comparing them. We all know in SolidWorks 101 how to extrude, revolve, and add fillets. So those are our basic features. They work very well, they're very powerful, they're very robust. When you start to use more of the advanced features like boundary, sweep, fill, planar surfaces, you can use those, by the way, in both a solid or a surface mode, but they take many more features to create. You can get much more exotic and swoopy shapes from them, but they're not basic modeling. And basic modeling just isn't enough for some consumer products to execute their shapes. So that's why we have this palette of many different features in SolidWorks to execute advanced shapes. And then I like to think of the basic advanced modeling features, but then there are modifiers to that. So you can, if it is a surface, then you can do certain things with it. You can trim and knit it. You can extend or put a ruled surface on it or offset it and do any combination of those. And oftentimes you have to do combinations of those to get back to your final solid form. So if you keep that in mind as you kind of, as I mentioned earlier, strategize out your plan of attack, try to use the left column as much as possible. Defer to the middle column and the ones I haven't shown to complete your advanced shapes, and you should be in good shape. Also, why you're doing advanced modeling in SolidWorks, you want to keep your eye on what you're creating as you're creating, because it's probably likely that the shape that you're creating is going to eventually have to be shelled, or you're going to have to do some overmoldings which require offsets, that while you're creating advanced shapes like boundaries and sweeps especially, you need to have a confidence that they're going to shell. And so a quick way to do that regularly as you're modeling is, while you're modeling features, do a quick offset of it. And do a quick offset of it by the kind of known shell dimension that you're going to be using. Sometimes you'll see that it won't offset. And it's because usually the shape that you created has a rate of curvature in it that, when offset, exceeds the rate of curvature that it can geometrically build the shape. SolidWorks shell is pretty good. It can even overcome some of this or allow it. But it's always good up front to know when you're kind of pushing the boundaries of what SolidWorks shell can do. So I think with that, we have a good set of information to move forward into the next episode and following episodes of our advanced modeling series. These are good to always bring up and keep in mind as we work with our advanced shapes. In our next couple of series, we'll start to get more into the actual features and how they're used. So with that, I'm going to conclude this episode, and we'll pick it up again in our next episode.
Thanks for tuning in to today's episode. We hope what you've learned has been informative and can help you to better use some of SolidWorks' advanced features. You'll see in the YouTube description a link to example models used in today's video. Feel free to download it, and you can explore these techniques at your own leisure. Also, we'd love to hear from you, so consider emailing me at the address you see here on the screen. If you need help on your design project or just want to know more about us, stop by our website at spannerpd.com or email us at hello@spannerpd.com. Take care, and I'll see you in the next episode.